The paper we choose is team9 Learning Transparent Object Mapping. And here is our brief introduction. In traditional image mapping, we assume a point color is a linear combination of foreground and background color. Transparent object mapping is much more difficult than traditional one. It needs to consider the environment light caused by refraction and reflection. In this paper, the author used a learning-based method to do transparent object mapping. And so let's look at related works. This paper addresses the problem of transparent object mapping. Existing image mapping approaches for transparent objects often aim to an accurate environment map. However, it will seek a huge number of input images to achieve a higher accuracy, or specially designed patterns to reduce the number of required images, which imply tedious capturing procedures and long processing time. Hence, a bunch of works try hard to find accurate environment map with as less input as they can. Exchange tried with CNN-based image mapping, and SK-Yun with interactive way, which requires users to manually mark the foreground and background in the image, and models the refractive effect using a thin plate spline transformation. However, all of these works can only reduce to the number in the order of hundreds and consume large processing time. The key point is that we don't need to produce an extremely accurate but a realistic one. It will be ill-posed if some way could produce accurate one with only one input image. For given the huge solution space, there may exist multiple objects and background that can produce the same refractive effect. Hence, the object of this paper is to introduce a simple and efficient model for transferring object mapping as simultaneously estimation of an object mask, an attenuation mask and a refractive flow field that can produce spatially realistic refractive effect from a single image, instead of estimating a high accurate refractive flow. We propose a convolutional neural network, TomNet, to learn an environment map of a transparent object from a single image. To the best of their knowledge, TomNet is the first CNN that is capable of learning transparent object mapping, and their TomNet has produced promising results on both the synthetic and real dataset.
So now let's look at proposed method. In transparent object mapping, we can form a formula like 1, where FB alpha denotes the foreground color, background color, and weight, respectively. The last term accounts for the environment light accumulated from n pre-designed image. Ri is a vector describing the contribution of light emanating from the eye's background image Ti, and Tiai denotes the average color of a rectangular region Ai on the background image Ti. Assume a single background image as the only light source. We can reformulate to formula 2. Assuming a colorless model, F becomes 0 and R becomes a light attenuation index. The formulation can be simplified to 3. We further introduce a binary foreground mask to define the object's region in the image. The equation can be rewritten to 4, where M represents background if M is equal to 0, M represents foreground if M is equal to 1. In equation 4, we can observe that the transparent image mating problem is reduced to solving M, Zo, and P, so we only left 3 unknowns. So in this paper, the author used learning method to do transparent object mapping. They present a 2-stage deep learning framework. The first stage, core stage, is an encoder-decoder network. The second stage, refinement stage, is a residual network. In TomNet, We want to generate a maze containing object mask, attenuation mask, and a refractive flow mask. In first stage, we will produce object mask, attenuation mask, and a refractive flow mask. In second stage, we will produce attenuation mask and a refractive flow mask. The main purpose of first stage, also called core stage, is to predict a robust object mask. The architecture of core stage is based on mirror-link CNN network, and it composed of one shared encoder and three distinct decoders. The main problem of first stage is that the estimated attenuation mask and the refractive flow field lack local structural details. To overcome this problem, the author introduced second stage, refinement stage. The main purpose of second stage is to achieve a sharper attenuation mask and a more detailed refractive flow field. It is a residual network that takes the input image and the output of coordinates as input. So now let's look at loss function for core stage. There are four losses defined in core stage: object mask segmentation loss, attenuation regression loss, refractive flow regression loss, and image reconstruction loss. Object mask segmentation loss is a binary classification problem, so we use binary closed entropy to define loss function. Attenuation regression loss is a mean square loss. Refractive flow regression loss is an average endpoint error (EPE). And image regression loss is we use MSE mean square error to measure the difference between input image and the reconstructed image. Finally, we add four losses together to train neural network in core stage. So now let's look at loss function for refinement stage. There are two losses in second stage: attenuation regression loss and refractive flow regression loss.
Now we look at experiments. Let's introduce their dataset first. Their dataset consists of synthetic dataset and real dataset. They created a large-scale synthetic dataset by using POV ray to render images of synthetic transparent objects. And we also collected a real dataset for evaluation. In synthetic dataset, it includes background images, transparent objects, ground truth maps, generation, and data augmentation. In real dataset, it was collected using 14 objects and 60 background images, resulting in a dataset of 876 images. We present experimental results and analysis in this section. Now we can look at Table 2. We evaluated EPE for refracted flow fields, IOU for object mask, MSE for attenuation mask, and image reconstruction results. We can discover that background was outperformed by a TOMNet variance with a margin for all the evaluation metrics, which clearly shows that TOMNet can successfully learn a map. If we remove each component from CrossNet, the overall performance decreased. And by introducing RefineNet, the refractive flow performance was boosted. It verified the RefineNet is effective. Now we look at Table 3. It shows the result on synthetic data. Similar to previous experiments, TOMNet outperformed background with a large margin, and slightly outperformed CrossNet in EPE and MSE. The errors of complex shape category are larger than that of others, because complex shapes contains more sharp regions that will induce more errors. It shows that our model can generalize well from basic shapes to complex shapes. Results on real data are shown in Table 4. We evaluate PSNR and SSIM metrics between each pair of photograph and reconstructed image. The average PSNR and SSIM are above 21 and 0.89. The values are a bit lower for complex shapes due to the opaque pace of complex objects, as well as the sharp regions of the objects
that might induce large errors. After training, team9 generalized well to common real transparent objects. The rest is our conclusion. This paper introduced a simple and efficient model for transparent object mapping which called team9. team9 takes a single image as input and predicts environment map as an object mask, an attenuation mask, and a refractive flow field in a fast-feed forward path. This paper also created a large-scale sensitive dataset and a real dataset as a benchmark for learning transparent object mapping. However, team9 cannot be applied to color-transparent objects with multiple mating. They want to explore better models and architectures to handle these scenarios as their future work. This is our presentation. Thank you.